A groundbreaking study has shown that we might have been wrong about the age of the universe. It suggests that the universe is almost twice as old as previously calculated, proposing an age of 26.7 billion years. This revelation emerged from analyzing data from the James Webb Space Telescope's first year of observations, where it utilized its remarkable capabilities to observe infrared light and explore the early universe, the edge of time. Webb's discovery of high-redshift galaxies, more massive than expected, has challenged our current understanding of cosmology, leading astronomers to question the mechanisms of galaxy evolution and even the occurrence of the Big Bang. However, by reviving a century-old idea, a study shows that we might have wrongly estimated the age of the universe itself. So what's the age-old idea that is able to explain the unusual galaxies Webb saw at the edge of time? What's the evidence in favor of a revised age of the universe? Finally, and most importantly, if the universe is really 26.7 billion years old, how does this impact our understanding of the cosmos? To understand this discovery, it's important to revisit the 1920s, when a single equation changed the course of astronomy. In the early years of that decade, the prevailing belief was that the universe remained static, showing neither expansion nor contraction. However, American astronomer Edwin Hubble's observations shattered that notion. He found that galaxies in deep space were actually moving away from us, and even more remarkably, there was a pattern to this motion. The farther a galaxy was from us, the faster it was receding. So if v is the velocity of recession and d is the distance to that galaxy, then v is directly proportional to d. This seemingly simple relationship gave birth to one of the most controversial numbers in astronomy, the Hubble Constant. It stands as a crucial parameter that describes the behavior of the universe, revealing the rate at which it is expanding. Assuming a constant rate of expansion throughout history, the galaxies moving away from each other must have been closer together in the past. By tracing back in time, we reach a moment when all matter and radiation in the universe would have been concentrated into a small region, the beginning of the universe, also known as the Big Bang, from which the universe rapidly expanded. This expansion's timescale is known as the Hubble time, corresponding to the duration of the universe's expansion, or simply the age of the universe. Mathematically, it's the reciprocal of the Hubble constant. Hubble's observations also unveiled an important consequence of the universe's expansion, the stretching of light, resulting in what we know as redshift. When a distant galaxy emits light, as it travels through the expanding universe, the light waves get stretched, causing a shift toward the red end of the spectrum. The farther the galaxy, the redder it appears. However, not everyone was happy with the idea of the expanding universe. One of them was the famous Swiss astronomer Fritz Zwicky. Zwicky was one of the greatest minds of his era. He was a brilliant astronomer who had predicted the existence of dark matter and neutron stars. He also pioneered the study of supernovas and cosmic rays. But Zwicky wasn't convinced by the way Hubble had interpreted redshift and concluded that the universe is expanding. He offered an alternative explanation, the tired light hypothesis. According to Zwicky, light photons lose energy through collisions with other particles during their journey to us, resulting in a shift toward the red end of the spectrum. This idea did not involve the Big Bang or the expansion of the universe. In the 1940s, the famous alpha-beta-gamma paper provided strong evidence in the support of the Big Bang theory. This paper demonstrated that elements like hydrogen, helium, and other heavier elements were created during the early stages of the universe, a phenomenon that could only be explained by the Big Bang. Subsequently, in the 1960s, The discovery of the cosmic microwave background, or the CMB radiation, became a landmark evidence for the Big Bang and the expansion of the universe. The CMB is the afterglow of the early universe, and its detection lent further support to the Big Bang theory, solidifying its place as the leading explanation for the origin of the universe. With the accumulating evidence and observations, the tired light hypothesis proposed by Fritz Zwicky lost its ground and eventually faded from the forefront of cosmological discussions. Currently, the behavior of the universe is elegantly described by the LCDM model, which stands for lambda-cold dark matter. This model portrays the universe as an accelerating, expanding system, incorporating the presence of dark energy and dark matter. It successfully accommodates key features of the Big Bang theory, as well as cosmological redshift caused by the universe's expansion. However, the recent observations from the James Webb Space Telescope have raised intriguing challenges to the LCDM model. By peering into the deep universe and observing the nature of high-redshift galaxies, Webb revealed aspects of the universe that the LCDM model struggles to explain. The problem lies with the redshift. In the present era, the universe has a redshift of 0, and as we move backward in time, the redshift increases. This means that objects at higher redshifts are farther away and represent earlier stages of the universe. The James Webb Space Telescope made significant observations that challenged the traditional LCDM model. It revealed fully evolved bright and massive galaxies at redshifts of Z equals 11 and 15, corresponding to an age of just 300 to 500 million years after the Big Bang. While similar galaxies at a redshift of 10 were previously observed with the Hubble Space Telescope, JWST's findings intensified the anomaly by providing data on multiple high redshift galaxies consecutively. The challenge arises from the predictions of the LCDM model, which suggests that stars start forming in the young universe when it's around 150 million years old, at redshifts greater than 20. It then takes about 1 billion years for the stars to fully form massive and bright galaxies. However, the high redshift galaxies observed by Webb do not conform to this prediction. If the stars indeed started forming when the universe was 150 million years old, it becomes puzzling how they could have rapidly formed large and luminous galaxies by the time the universe reached an age of 300 to 500 million years. This discrepancy is known as the impossible early galaxy problem. Naturally, some astronomers questioned the occurrence of the Big Bang, and others wondered if there was any missing link in the star and galaxy formation mechanism. The conundrum is that there is observational evidence for the existing theories, so no one knows where the science is going wrong. But, as it turns out, the simplest explanation could be the miscalculated age of the universe. And this is where the forgotten idea of Fritz Zwicky re-enters the scene. You must be familiar with the concept of angular size and angular diameter distance. If we know the angular size and the physical size of an object, we can determine how far it is, or the angular diameter distance. Also, from daily life experiences, we know that as a distance to the object increases, its angular size decreases. The same principles apply to galaxies in deep space, but up to a certain limit. As we observe galaxies at greater distances, their angular size appears to decrease gradually until we reach a turning point at a redshift between 1 and 1.5. Beyond this redshift, the angular size starts to increase again because the expansion of the universe becomes more pronounced. Now this is where Webb found a discrepancy. The currently accepted LCDM model predicts a turnover at a redshift of 1.5, but Webb observed a turnover at a redshift of more than 10. To address the discrepancy and tackle the impossible early galaxy problem, theoretical physicist Rajendra Gupta from the University of Ottawa has proposed a novel approach. Of course, Zwicky's tired light hypothesis alone cannot explain Webb's observations because it lacks the expansion component. Therefore, in addition to the tired light hypothesis, he introduces an idea called the Covarying Coupling Constant, or the CCC model. According to this model, the fundamental constants such as the speed of light, Planck's constant, and the gravitational constant are not constant in time. Instead, they undergo variations that extend the timeline of the universe's evolution. By incorporating the CCC model alongside the tired light hypothesis, Gupta's work provides a unique perspective on the challenges posed by the observations of early galaxies. This approach stands apart from the LCDM model, where the accelerating universe is described by a constant lambda. Instead, the CCC model introduces another constant that accounts for the dynamic evolution of fundamental constants over cosmic time. To assess which model aligns best with the observations, he examines several possibilities: the tired light model on its own, the combination of tired light with the CCC model, the combination of tired light with LCDM model, the LCDM model in isolation, and an alternative version of the tired light model. Among these, CCC plus TL and LCDM plus TL are of utmost importance. And the reason is this graph. It's a plot between the redshift and angular size of the galaxies. The blue marks represent the galaxies observed at different redshifts before the James Webb Space Telescope, and the red ones are the Webb galaxies. The different curves show how the angular size of the galaxies varies according to different models. As you can clearly see, the currently accepted model, the LCDM model in green, shows a turnover at a redshift of about 1.5. Beyond that, it significantly deviates from the redshift of the observed galaxies. However, the angular size for the CCC plus TL model, shown in dark blue line, became smaller and smaller until beyond z greater than 10. It not only matches the observations made by telescopes before James Webb, but also aligns with the high-redshift JWST galaxies. In addition to comparing the theoretical models with observational data, the analysis also involved examining the physical size of objects predicted by each model. Interestingly, the CCC plus TL model demonstrated an advantage in this aspect as well. According to it, the size of objects at higher redshifts was found to be 15 to 20 times greater than predicted by the LCDM plus TL model. This disparity in object size provides a plausible explanation for the observed massiveness of high-redshift galaxies. Further supporting the viability of the CCC plus TL model in addressing the challenges posed by the early universe observations. According to the CCC plus TL model, the universe would be 5.8 billion years old at a redshift of 10 and 3.5 billion years old at a redshift of 20. This extended time frame allows more opportunity for galaxies to form and evolve into massive and luminous structures, providing a more favorable explanation for the observed properties of high redshift galaxies. Out of all the basic and hybrid models considered in the study, the CCC plus TL model has demonstrated superior capability in explaining the observations. Its combination of the tired light hypothesis and the Covarying Coupling Constant concept has resulted in a more accurate match with the data. If indeed the universe follows the CCC plus TL model, its estimated age would be approximately 26.7 billion years, which challenges the previous calculations and indicates the potential for a revised understanding of the universe's timeline. However, science cannot be tweaked to match the observations. Being said that, there are some loopholes in the hybrid theory of Covarying Coupling Constants and tired light. If these constants were indeed fluctuating in the early universe, their effects should also be observed in current-day experiments on Earth. However, numerous experiments have provided strong evidence for the constancy of these fundamental constants over time, up to more than 1.7 billion years. Furthermore, the tired light hypothesis, when combined with the CCC model, might alter the spectral properties of the cosmic microwave background. Since CMB has been extensively studied and measured, Any significant deviations from its isotropic nature could pose a significant challenge to the CCC plus TL model. Nevertheless, with the JWST posing challenges to the traditional LCDM model, astronomers are actively exploring alternative ideas. It will be interesting to see which model fits the future observations that different space telescopes bring to the table. This concludes another episode of the Sunday Discovery series, so if you've enjoyed watching it, make sure to subscribe to our channel and press the bell icon so you don't miss any future episodes of the series.